Okay guys, I am here to do a quick little review of one of the key concepts that we've been working with this chapter, and that is variation. So there are all sorts of variation. These are sort of four basic ones. We've got a direct variation, and that's simply when one quantity gets bigger, the other one also gets bigger in a linear fashion. If we were to graph it, a direct variation is something that just goes through the origin and goes up with some slope. Well, that slope is our constant of variation, it's called. So that does not change, hence the whole concept of constant. Anyway, so we've got this slope and a straight line, and that's one of the most straightforward types of applications that we've got for this. Think of like your hourly rate working at a job. Okay, if you've got a babysitting job, you get paid $7 per hour. Each hour you work, you go up by $7, and you get that linear relationship. Okay, inverse, this is the one that's a little bit harder to wrap your head around, because it's as one quantity goes up, the other quantity goes down, but it's not in a straight line fashion. It's not just a line with a negative slope, okay? It goes like that. This is one in which the product of the two variables, you get some point here, we'll say x and f of x. These two data points, if you multiply those together, you get the constant. If we divide one side by x, we get f of x equals k over x. All right, that's an inverse variation. The third one is a direct square variation. Try to ignore this word because it appears up here. If it's just standard direct, this is the straight line. If it's direct with the square, what it means is one quantity gets bigger, the other one gets bigger by the squaring of that amount. And the same with the fourth one, it's a direct cube. Again, that's the critical word. And you will be told in most of the sample problems the type of variation. We're not really exploring how you determine the variation, you're usually told it. Okay? So that's the square, and that's the cubic variation. Again, all of the k's here stand for a constant, a variation that we will solve for, and that we use to make a prediction. All right? The graph of the square is going to be like half a parabola like this, and for a cubic it's going to be much steeper. If you could see the other half of a parabola, it would go like this, but the other half of a cubic will go like that. So there is a difference. It's not that they are the same. Okay, so let me try a little example then. Suppose we happen to know that a certain wind generating turbine will make a certain amount of electricity. Okay? Wind is a volume. It's a three-dimensional quantity, so it turns out that it's a cubic variation. Okay? So we say, suppose that a 7 mile per hour wind will produce 900 kilowatts of power. Okay? That's like a basic data point. We happen to know that wind generation is a cubic variation. All right? So then we're asked, how much power will 18 mile per hour wind produce? That's one question. Another one might be, suppose I have a target of 2,000 kilowatts. All right? If 200 kilowatts is being produced, then what is the power? What is the wind speed? Okay, so two separate questions, but both of these will solve sort of the same way. All right? The first step, the first thing I'm going to do is I'm going to write what I'll call a basic equation. All right, and you can basic equation. That's the one that would be from one to the four that I just gave you in the previous frame. So in this case, I tell you it's cubic, so you write y or f of x equals kx cubed. All right, and then the second step is we're going to have what we call a working equation. That's where we replace these letters, the x and the y, or I should say, from the previous example, I wrote it in function notation, f of x. All right, I'm going to replace these two variables with what they refer to sort of in the example that I've given you. Okay, in this case, the power that varies according to the wind speed, s, is equal to ks cubed. All right? So this just makes it a little bit easier to keep track of. We realize we're talking about power that's going to depend upon the wind speed. All right, well then I sub in my first data point, and that is that I happen to know that when the S is 7 miles per hour, it will produce 900 kilowatts of power. All right? The thing that does the varying is always the thing that's by itself. So if we say power varies with wind speed, make sure that this is the thing that's by itself with equal sign, and then the thing that makes it vary has the constant. So that's 900 right there will be equal to K times, in this case, the wind speed is 7 cubed. All right? Well, I just need to solve for K. So K is going to be equal to 900 divided by 7 cubed. All right? So I can just divide by 7 times 7, which is 49, times 7 is 343, is going to give me my K when I divide both sides by that. And I can leave it in that fraction form. There's nothing wrong with doing that. I can also work out the decimal. It's going to be a little bit less than 3, so 2.7 or something. But I'll leave it in that form. Okay, so then the third step is to replace, in this step number 2, my working equation, replace K. So I'll say then P of S is going to be equal to 900 over 343 times S cubed. Okay, that is my equation that will allow me to solve the first step, the first problem. How much power will an 18 mile per hour wind produce? So that will be then P of 18 is going to be equal to 900 over 343 times 18 cubed. Okay? So I don't have a calculator, so I'm going to go grab one and I'll be right back. Alright, that didn't take long. Clear that. And I take 900 and I divide it by 343, and then I take that and I multiply that times 18 to the third power. 18 caret 3, and I'm going to get 15,303 when I round. That is going to be approximately 15,303 kilowatts. So you can see the wind has gone, what we think of maybe from 7 to 18 as not being a huge jump, but the amount of power has gone from less than 1,000 to more than 15. That shows how an understanding of this cubic relation is really important, because if we had to guess, we might way have underguessed that. All right? The second equation then is how much, if I know I'm generating 2,000 kilowatts, all right, of wind, 2,000 kilowatts, what is the wind speed? Well, I go back to this equation, I just fill in 2,000 kilowatts, and I know that that's going to be 900 over 343, and then S to the third. And I just need to solve this. I'm going to divide both sides by 900 over 343, or multiply by 343 over 900. That's my reciprocal. All right. So I can do that really quickly. I get 2,000 rather, times 343 divided by 900, and I get 762, and then I need to take the cube root of that. So I go to math, I hit option number 4, I get the cube root symbol, and then I do second answer, and that's down there, it's the negative sign, close the parentheses, and I get 9.13 miles per hour. So S is equal to approximately 9.13 miles per hour. Okay, so to go from 1,000 up to 2,000, the wind speed only has to go up by a little bit more than 2 miles per hour. Okay, so in all of those 4 types of variation, the idea is the same. Sub in the one data point, solve for the K, the constant, replace the constant with what you found it to be, and then solve the final step of the problem to make that prediction. All right, good luck.